grams of hot. The first thing is we need the T hot. What did you get up for your T hot?
67.9.
67.9. Right, let's do this. 67.9 was the hot, okay. What was your mix?
42.5.
42.5. And what was your cold?
22.2.
22.2. Okay, so what's your delta T hot?
42.5.
And what was your delta T cold?
20.3.
Yeah. This is impossible to get a positive heat capacity of the calorimeter. Because if you think about this, the hot water, 50 grams of hot water, if you only had 50 grams of hot water and 50 grams of cold water, then the hot water will cool down and the cold water would warm up by equal amounts because it's 50-50 mix, and so they're going to go right to the center of the temperature range. And so, like, if you had 100 degree water and 50 degree water, it should mix at 75. It's a 50-50 mix. But in this case, you have a calorimeter that's hot and hot water. And so what's going to happen is since you have hot water, then what we expect is that the cold water should warm up a little bit more because it's absorbing not only heat from the water, but it's also absorbing heat from the calorimeter. So it should warm up a little bit more than the drop here. And so this delta T cold has got to be bigger than delta T hot. Otherwise, it's never going to come out negative. In other words, what you have is you have a scenario where the calorimeters, for example, if you put a cold cup of coffee inside inside a coffee mug, it would warm up. That's the type of scenario. And so I would just look at the graph some more and then see or something else. Something else happened. But your calculation is probably okay. It's just something with the data. This is why I wanted you guys to graph it in lab, and then I could take a look at your graph and then see, because this type of situation happens quite frequently where people will get a negative heat capacity of the calorimeter. Sometimes it's due to how they graphed it, sometimes it's due to their calculation. So I was hoping to see everybody's graph yesterday so I could see what was the situation. But anyway, I could take a look at your graph, but not now. Okay, any other questions? I need to post these notes here on Canvas. I'm sorry? Oh, that's right. I need to give you back your retake. I have those. I forgot to give those back to you. Oh, did I? Which test are you talking about? Oh yeah, it's graded. So I think what I'm going to do is there's a lot of PowerPoint slides. PowerPoint slides. 70 PowerPoint slides as well. So for this chapter, I'm going to switch over just to notes. We'll hit some of the PowerPoint slides. But we're looking at this one. So this one, what we call a system or surroundings, it doesn't matter. All you're looking at is for, energy or heat to be transferred from one to the other. So sometimes, we'll put this is our system. Sometimes we'll put that. In this case, we'll just put the hot lead. So this is an idealized experiment. It's not practical. So if we remove the hot lead from the boiling water, the hot lead's at 100 degrees C. What's going to happen immediately when you take it out of the hot water? It's going to start giving off heat to the surroundings, but we're not measuring that heat that's going into the surroundings there. And so this is kind of why we were monitoring things, and we try to do this quickly. But anyway, the heat that was giving off to the surroundings, we were monitoring that with our temperature, curve or something like that. Even then, it's difficult. So anyway, what we're going to do is we're going to take the hot lead out of here and then just dump it into this cold water. Okay, in the process of taking this hot lead out and dumping it in the cold water, by the time it hits the water here, it's a lot colder. And so this is why I reversed it. I think it would be better if we took the cold water and dump it into the hot lead. That way there's less of the heat drop. And so this is why in the lab I reversed it from the procedure. But anyway, getting back to this, since this is some hypothetical experiment, we're going to imagine that nothing's happened. When this lead hits the water, it's at 100 degrees C. Okay, there's another hypothetical thing here. And this beaker is so well insulated that, this would be the calorimeter. So we have the water here. So the surroundings are going to be the water, 50 grams, plus the calorimeter. And normally you'd expect, okay, the heat from the lead is going to warm up the water and it's going to warm up the calorimeter, including the thermometer. But what we're going to imagine is that the thermometer and the calorimeter, the calorimeter includes the rest of the universe because heat can leak out into the rest of the universe here. The heat capacity of the calorimeter is 0. If the heat capacity of the calorimeter is 0, it doesn't absorb any heat at all. It's a perfect insulator. And so when we dump this lead into the water, the only thing that's going to absorb the heat will be the water. And so what we can do is we can determine how much heat the water absorbs because we know the specific heat of water. Specific heat of water tells us the relationship between the temperature change and that. And so this is, I think, did we finish this problem? Oh, I guess we finished it. All right. So I was behind in the afternoon class. So when we look at the specific heat, that's actually a pretty low specific heat. Metals tend to have pretty low specific heat. It only takes 0.133 joules per gram per degree C to heat up. So if you were to heat up a metal like lead, it heats up rapidly. Let's see the range of specific heats here. And so we should know what's high, what's low, as far as specific heats go. So when looking at specific heats, lead is pretty low, 0.13. Is there anything lower than lead on this? Gold is pretty low too. Copper is a bit higher, 0.385, but still copper is pretty low. So if you have a copper pot, it heats up quite rapidly. Iron takes a little bit more heat to warm up than lead or copper. Then we go on. Water, this is solid water, so that's ice. Specific heat of 2.11. If we look at liquid water, it's 4.18. We call that fairly high. Water has a fairly high specific heat. That is, water acts as a good heat sink. So when you work with, when I was working with hot metals, sometimes you'll just quench them in water because water can absorb a lot of that heat and cool it down rapidly. In biological processes, it's very important. Water has a very high specific heat. In other words, you have to add a lot of heat, a lot of heat in order to get it to warm up. Why do you have to add so much heat? Well, water has lots of ways to absorb that energy. Can absorb that energy as kinetic energy. The water molecules themselves can vibrate, they can rotate, and they can translate. And so water has a lot of ways to absorb that. Some of these other complex molecules, ethanol, is fairly high, 2.44, but not as high as water. When you go down, this is surprisingly high. Take a look at the specific heat of hydrogen gas. Yeah. And so these are our observations. And so typically what we know is water is fairly high and metals are really low. There are other things that are fairly high, more complex molecules. It's like the more complex the molecule is, the higher the specific heat. But we look for patterns, and then we look, what's the explanation for this? So we might come up with a hypothesis. Why does hydrogen have such a high specific heat compared to, let's say, steam? You'd expect steam to have a fairly high specific heat, but it's only 2.08. Steam or ammonia, as a gas. And so when we look at these observations, we look for patterns. And then if you understand the patterns, then you could make predictions about relative specific heats. Which one do you expect to have a higher specific heat? You'd be able to answer those types of questions. So when we get a chart like this, initially we just look, what's the range of specific heat? The range is 14.3, but this 14.3 is somewhat of an outlier because the bulk of them lie a lot lower. And so those are the types of things you notice. Of course, we're not going to get into the theoretical part of this until later. All right, for calorimetry, what we do with calorimetry is we measure. What we measure is Q. Like this calorimetry, we measure Q of an object. The object being lead. How much heat is given off the lead, hot lead, into cold surroundings. And so, but we can also measure Q of the reaction. And so heats of reaction in calorimetry and objects. So we looked at, in 7.2, we looked at objects, I guess. Hot and cold objects. And calorimetry. So in calorimetry, we measure two things. We either measure Q of the object, like the lead, how much heat was lost by that hot lead, or we measure Q of the reaction or process. A process would be a physical process, like melting or boiling or something like that. How much heat does it take to melt? We can measure that with calorimetry. How much heat does it take to boil? Or how much heat is released when steam condenses? This kind of stuff. And so these are the two types of things we measure. When we're doing an object, we're looking at transfer of kinetic energy. So we have a hot object. Okay, let me just do this here, down here. Q of the object. When we're looking at an object, we're transferring kinetic energy from the hot to the cold object. And what we call the system and surroundings doesn't really matter. However, when we're doing a process or reaction, then what we're doing is we're transferring the potential energy as kinetic energy to the surroundings. The surroundings is an object. However, our system is a process. And so we have chemical potential energy. Let's say we have methane and oxygen at room temperature, and we combust it. It's going to get hot because the surroundings will get hot, but then the methane and oxygen system changes from methane and oxygen to CO2 and water, a product plus energy. And so that's where we go from potential energy to kinetic energy in the surrounding. So we're transferring heat in this sense. And so over here, this would be like, say, minus Q of the object. This would be what we call as minus heat of the reaction or process. So we'll just say reaction process. So that's what we're losing there. We'll go up from this potential energy here. So in calorimetry, we either measure the this kind of exchange of temperature, heat, or we look at a reaction, and all that energy goes into heating up the surroundings.
Is the heat reaction Q RXN or RXN?
RXN. RXN is just abbreviation for reaction. And sometimes your books will just read it as R, and that just stands for reaction. But I'm putting RXN instead of R. So we want all the potential energy to go into the surroundings. In order for all the potential energy to go into the surroundings, we have to make sure everything cools back down to where we started. So if we start at room temperature, we need to end at room temperature. And so what we care about is the initial and the final. And then in between, what happens is lots of heat. You know, when you combust methane, it goes up to like almost 1,000 degrees C, let's say. But we don't stop there. When we combust methane, we start off at room temperature, goes up to about 1,000 degrees C, and then cools down. As it cools down, it's dissipating heat, and then we're back down to room temperature. Okay, so this is called a state function. A state function is all we care about are the initial and final states. We don't care about the in-between. Well, we do, because the in-between is what heats up the surroundings. This is what's going to heat up the calorimeter here. That's an exothermic reaction. With an endothermic reaction, it's going to absorb heat to go to product. And so, you know, the temperature is going to drop, it's going to get cold, but then we just wait for it to restore back up to room temperature. And then we know the maximum amount of heat that will be absorbed. Because if we stop when it's cold, then it needs to absorb more heat, more energy to get back up. And so again, we just look at the initial and the final. So this is just saying, you know, if it gets hot, wait till it cools back down to room temperature. If it gets cold, wait till it warms back up to room temperature. So this slide is just trying to show an exothermic reaction. This exothermic reaction is getting hot. So we just wait, you know, if we want to figure out the maximum amount. If we're doing calorimetry, this is not calorimetry because we need other things, you know, to do calorimetry. But we just wait. It rose up to 40.5, and then we just wait till it goes back to RT, room temperature. That's exothermic. In an endothermic reaction like this, the temperature drop down to 5.8 C, and we just wait until it goes back up to room temperature. Calorimetry, we want to measure how much heat, you know, was transferred. So in calorimetry, we'd have a calorimeter. The calorimeter, we can monitor, you know, how much heat was dissipated from our reaction into the surroundings, you know, which is our calorimeter, basically. Sometimes it's more than our calorimeter. You know, sometimes the surroundings is a bit more than the calorimeter, like in this case, in the case in our lab. In this case, the surroundings was the 50 grams of water plus the calorimeter. In the homework, you have two types of homework problems. One type of homework problem is saying the calorimeter is the perfect insulator, and so you can completely ignore the heat loss of the calorimeter because the heat capacity of the calorimeter is 0. That's an assumption. That's not reality. That's like ideal gas type thing. And then in the more advanced problems, then they say, well, that's not really the case. A little bit of heat is going to be lost to the calorimeter. Right? And so you'll notice that in the homework. There are two types of homework problems dealing with calorimetry. One, where they assume the calorimeter doesn't absorb any heat, and therefore all the heat goes into the water here that's sitting inside the calorimeter. Or two, you have to do it like we did it in the lab yesterday, where the calorimeter does absorb some heat. So this is just a slide reminding you that the initial and the final temperature must match when we do cube reaction. Otherwise, you aren't getting all the heat. No. Because if it's still hot, some heat's going to be dissipated. If it's still cold, some heat's still going to be absorbed. So we've got to make sure that the initial and the final temperature are the same. Otherwise, we're missing some energy. We have different types of calorimeters. And this is called a bomb calorimeter. This whole thing is the calorimeter here. And that's the surroundings. This water is also part of the calorimeter. So we don't have to weigh how much water this is. What you do is you just dump a whole bunch of water in there, and then we calibrate the calorimeter. Inside here, this is called the bomb. And the bomb is for like combustion reactions. Like if you have a combustion reaction, are you going to do it in a styrofoam cup? No. And so what we're going to do it in is a steel bomb. So let's say we're going to burn some sugar, and we want to figure out how much energy is. Let's put like 5 grams of sugar here. If we put in 5 grams of sugar and burn it, how much energy do we get from combusting 5 grams of sugar? Okay, so the first thing we need to do with a bomb calorimeter is we need to calibrate it, because we're not going to weigh how much water this is. We're not going to weigh how many grams of glass that is. We're not going to weigh how many grams of iron this is. We're not going to weigh how many grams of air are in the rest of the universe. What we're going to do is we're just going to burn something that we know. We know what we call the heat of combustion. So if we know that, let's say, 1,000 kilojoules of energy are released for every gram burned, then we know how much heat. That's our standard. It's called our primary standard in this case. So we weigh out the sample that gives off a known amount of heat. We burn it in here and then see what the temperature rise is. And then all we do is we take the Q, the amount of heat that we calculate. Let's say we burn 5 grams. 5 grams times 1,000 kilojoules per gram means 5,000 kilojoules of heat were released. And then we measure the delta T. So we'll take the Q divided by the delta T, and that gives us joules or kilojoules per gram. Not per gram, sorry, per steel, per bomb. And so the first thing is we calibrate the calorimeter. This calorimeter consists of the bomb here, all the water here, the stir, the wires, thermometer, everything. And so we need to calibrate this just by putting a standard in here that gives off a known amount of heat. Once it's calibrated, then we can put an unknown in here. We put an unknown here, burn it, figure out what the temperature rise is, and then we can determine how much heat was transferred to the surroundings from that. All right, so the type of heat this measures, a bomb calorimeter measures what we call QV. This V stands for constant volume. If we're under constant volume conditions, then what's applicable? Dalton's law or Avogadro's law? Dalton's law. Dalton's law is applicable. So let's say we burn this in some gaseous form. This is why they call it the bomb. Then what's going to happen to pressure? If gas is formed during combustion here, then the pressure goes up. This is why they call it a bomb. They call it a bomb because they don't want it to explode like a bomb. Because what's going to happen is Dalton's law says the pressures are going to be additive. So the more gas we form in combustion, the higher the pressure is going to be, and the risk of explosion is there. So we have to be careful. We don't want to generate so much gas that it explodes. It depends on the combustion reaction. How many moles of gas are produced? Like 2 moles of gas, 3 moles of gas. How many moles of gas? Because each mole of gas has a volume of about what? Just roughly. At room temperature and 1 atmosphere. 2297 is STP. I want RT 1 atmosphere. No. 24.5. So roughly 25 liters. So, normally, if we form, let's say we just form 1 mole of gas extra in this combustion, we're taking oxygen, there should be oxygen here, so we're consuming the oxygen, and we're forming CO2. Let's say we form 1 more mole of gas than we have there. That means the volume should expand by 25 liters. Can the volume expand by 25 liters here? No. And so this is why they call it a mole. Let's say we end up with 1 mole less gas. So, the O2 combines and we form 1 more mole, fewer actually, 1 less mole of gas. And that means the volume should contract by 25 liters. The volume contract by 25 liters in a bomb? No. So this has to be a heavy wall. This is too thin because if you have the volume collapsed by 25 liters, then it should just crush. We should have what we call an implosion. So the bomb is to prevent explosions and implosions from happening because of Dalton's law. The pressure is going to either increase or decrease depending on how much gas is formed or how much gas is consumed in the particular combustion reaction. Does that make sense? And so this is why we call it QV. And it's QV because it's constant volume. And so we call this constant volume calorimetry. Okay, it's 1017, so 1017, I don't know why it hasn't gone off yet, but 1017 on 1017 is the time it's supposed to go off. If you haven't experienced this before, the alarms are very loud in this building, Chem building. Oh, did they? Oh, I'm going to ignore it until we're forced out.
It was interesting. 1017, 1017.
All right, now we're going to the coffee cup calorimeter. Coffee cup calorimeter, obviously we're not going to do combustion in this. Of course, they have other types they have things that are much more expensive than these coffee cups and that are better insulators. But this is the standard calorimeter in Chem 1A type labs. But the coffee cup calorimeter measures something different. The coffee cup calorimeter measures Q sub P. Do you know what the P stands for? The P stands for constant pressure. Sometimes Q sub P and Q sub V are the same thing. So let's say I had a special coffee cup and I was able to burn stuff. Sometimes QP and QV are the same for the same reaction. But sometimes they're different. So I need to write that over here. For us, it doesn't matter. If we did our reactions that we did yesterday in a bomb, like say we made a gigantic bomb where we could fit inside there, then it wouldn't make a difference. Because when you add 50 milliliters of water to 50 milliliters of water, are you going to expect a big volume change or anything and generate an explosion or implosion if the volume shrank? No. And so sometimes QV and QP are the same. Sometimes they're different. Yeah.
Pressure and high increase pressure, does it explode if you add the pressure, the high pressure inside the water? Because you change the pressure from outside from the surroundings inside. Like let's say for example it's kind of warm.
Yeah, I mean, if there's a big difference in pressure between the surroundings and the system, then you can have explosions occur. Even if it's water, like one mole of water is 18 grams of water. 18 grams of water occupies how much volume? It occupies 18 milliliters. If you convert that 1 mole of water into a gas, then you'll have 1 mole of gas. 1 mole of gas under room temperature and 298 is going to occupy what volume? About how many liters? About 25 liters. So you're going from 18 milliliters to 25 liters. How big of an expansion is that? It's pretty big. And so it's going to make a difference. What you have is this. If you did that in a coffee cup, no big deal. I mean, we were boiling water on the hot plate. Did you feel that? Did you feel the change in volume?
No.
You didn't feel the change in volume, right?
No.
Maybe.
But when it
Not sure.
comes to maybe when it comes to the surrounding around the cup, you can feel that it's like maybe hot or something.
Sometimes, yeah. We'll talk about that. It depends on the conditions. You didn't feel that because this is just in the open air.
Wait, so do they measure at a constant volume or temperature, or are they measuring a constant?
No. So if you put 18 milliliters of water in here and you boil it, then that water wants to expand to 25 liters. Is it possible to expand to 25 liters in this bomb?
No.
No. And so it's stuck. It's stuck in whatever volume this bomb is. That's what it's stuck to. And so what's going to happen is the pressure is going to increase. So we're going to see that. And so it depends on this. We have to know, are we doing this in constant volume conditions, or are we doing this under constant pressure conditions? Well, we don't know because it depends. Are you doing it in the bomb, or are you doing it out in the lab? And so most reactions occur in a bomb, or most reactions occur in the lab? Most reactions occur in the lab. And in the lab, when you do a reaction, do you do it in a bomb? No, you just do it right. We don't do it in a bomb. And so if that's the case, then what happens is if you generate a gas, what happens to that gas? I mean, we didn't really feel it when we were boiling the water, but you know who felt it? We didn't feel it, but do you know who felt it? The surroundings felt it. Because the surroundings had to make room. All of a sudden there's 25 more liters. And so the surroundings had to feel it. And this is kind of weird, but the surroundings had to make more room for this. So this is KClO3, which is called what? Potassium chlorate. And we heat it up. I'll throw in some catalyst in there and heat it up. So right now they're saying the pressure is 0. This is a vacuum, I guess. And what's going to happen is when you decompose this, you're going to form oxygen gas. In order to maintain constant pressure, what we have to do is we have to increase the volume. This is Avogadro's law. The volumes are going to be additive. And so whatever volume I had before, now I have to add additional volume because of the oxygen gas. We saw that when we did water displacement. We made some additional volume. So think about when you blow up a balloon. If you were to blow up a 1 liter balloon, does it require work or no work? Yeah, it requires work. And so there's work. This is called pressure volume work.
When you blow the air inside the balloon, it is like pressure volume work?
Yes. When you blow up a balloon, that's called pressure volume work. pressure volume work is required to maintain constant pressure for reactions that generate or consume gases. To maintain constant pressure for reactions or processes that generate or consume gases. So for example, if we did this in a bomb, what you don't want to do, let's say when you're heating the KClO3, you sealed it with a stopper that didn't have a hole in it. What would happen? What would happen is the pressure in your test tube would increase, and if your stopper is on there really tight, your test tube might have exploded. But most likely what's going to happen, and it happened I think to somebody in this lab or the other lab, the stopper pops off, right, and shoots out. And then you have to repeat the experiment. But if you do this in bomb conditions, then the pressure is going to increase here. You got to worry. You're creating a pressure bomb if you're generating oxygen gas. So to maintain constant pressure, we have to expand the volume. In order to expand the volume, that's like blowing up a balloon, because the atmosphere, we're under an ocean of air. We're okay because we can walk through the ocean of air, and it doesn't bother us, right? It bothers us when we don't have an ocean of air. So if we go up to high elevation, then we'll feel it. We need to be like, we're like fish. We need to be under the ocean of air. If you go too high up in the atmosphere, you're going to be in trouble.
Because the pressure increases.
No, being too high up, the pressure would decrease. There'd be no more air left.
I guess we go more.
So
The more we go up,
the more we go up, yeah. So this is it. How much work we have to do to blow up a balloon depends on how deep under the ocean of air we are. Have you ever tried to blow up a balloon, like say 10 feet underwater? Would it be easier or harder or the same?
No,
It's going to be a lot harder, because under 10 feet of water, you're like under 1.3 atmospheres or so. At sea level, it's going to be harder than like at the top of the mountain. At the top of the mountain, it's easy. Like if I drive up to Big Bear, and I have a bag of chips or something, it's like ballooned out. It wants to blow up, basically, or a drink or something. When you go up higher in elevation, it's easier to blow up than lower elevation. Eventually, it'll equilibrate. And so it depends on the amount of work you do depends on how big the balloon is and under how much pressure you have to blow it up under. That's the amount of work. So we can figure out the amount of work. We can calculate the amount of work by relating it to mechanical work. So let's say the gas is here and we want to expand, make more room for the gas to maintain constant pressure. So what they did was they just removed one of these masses and let the gas expand. Well, if you remove one of these masses, then we just have this mass, the single mass, and that single mass is going to be lifted up by h, the height here. And so what we know is the amount of work is equal to force applied on an object times the distance you move that object. And the force is going to be given by the mass times the gravitational constant, mg. And it depends, the distance is going to be given by h, or delta h. And so this is mg delta h. Mg delta h is the amount of work you're going to do for this particular thing. Well, if we multiply delta h by a and divide this by a, so we're multiplying and dividing by a, then m times g is the force over unit area. Force over unit area is pressure. And delta h times the area, that is the height times the area is the volume. And so we get this equation. This equation will allow us to calculate the amount of work that's done quite easily. All we need to know is the initial volume and the final volume, and then we can determine how much work is done. So going back to this slide here, we can figure out Okay, let's say we did 1 liter, we blew up a 1 liter balloon against the pressure of 1 atmosphere. So I'm just going to say, okay, let's say the volume of expansion here is 1 liter. I think we're okay, although I don't know. Maybe we should get out. We'll get out right when they let everybody back in. I think the windows are so tinted they can't tell. But if there is an earthquake, though, you would try to duck and cover. Yeah. In the lab, what you want to do, you got to watch out for things breaking, glassware, and this kind of stuff. If there's a fire that erupts in the lab, just go out. Don't try to extinguish the fire. The lab is built to contain the fire just inside the room. The doors are rated, I think, for 4 hours. And so, yeah, just watch out. And then if there is an earthquake or something, then watch out at the stockroom. There is a shutter there that comes down. That's for fire protection too, because they don't want a stockroom fire to get into the lab. And those shutters are automatic, like a guillotine. They'll come down. And so if there is some kind of emergency, don't put your hand in or your head into the stockroom window because the shutter will come down. Also, if you try to escape out of the windows in the lab are also designed to seal themselves. So if the fire alarm's ever triggered, if the windows are open, they'll automatically shut. So you can't open the windows. You have to escape out the doors. There are 2 doors in each.
I don't think they can see us.
Can you go back to the equations?
Yeah, we can go back to the equation. Which equation?
Those ones. What does A stand for?
Area. And so it's just to relate these. This is like thermodynamics. This is classic thermodynamics. Thermodynamics is you want to know a lot of different equations so you can come up with a lot of thermodynamic relationships. There are thousands of equations, seems to be. A lot of these you can try to derive. Others are more difficult to derive. Mm-hmm.
So why is the gas inside of a bag of chips expanding inside?
Because if I had the bag of chips at sea level, I have 1 atmosphere pressure. But as I go up and climb up the mountain, did I just sign this homework problem? What happens to the atmosphere density as I go up? Big Bear is like a mile high or so, 5,000, 6,000 feet elevation. And so the air is thinner there. When you try to breathe, you can feel the air is a lot thinner there. It's a lot less dense. We have an equation for this, how the pressure, actually this is in chapter 6. Talk about that. I'm not sure when to make our. Are you guys okay with not doing the evacuation drill?
Yeah.
If you prefer to do it, you can. So that's good because when they throw the fire alarm off, then they have to call the fire department in because the fire department's the only people who can shut it off. And sometimes that takes a long time. Sometimes it's quick. So I'm glad they're not throwing the fire alarm. But when they threw the fire alarm, nobody could stay inside. It's just too loud. This is a homework problem I usually assign, but I'm not sure. I think Master and Chem didn't have it, and so I decided I'll just not assign it this semester. but it's a good one to know. If you ever want to calculate the pressure, you can. So I don't have to go out and drive up to Big Bear with my barometer and then read the barometer in Big Bear. What I can do instead is I can just figure out what the elevation is. So we have noted that atmospheric pressure depends on altitude, so it depends on the height. Atmospheric pressure as a function of altitude can be calculated with an equation known as the barometric formula. And so this is the barometric formula. In this equation, P is the pressure of Big Bear. P naught can be any pressure in any pressure units. P naught is like your standard pressure at sea level. And so P naught is the pressure at sea level. But you can use whatever units you want. Generally taken to be 1.00 atmospheres or its equivalent. The units in the exponential term must be SI units. However, use the barometric formula to estimate the barometric pressure at the top of Mount Everest. So this is what I did. When I calculated, I didn't go up to the top of Everest with my barometer. I just calculated what the pressure should be. It's about 1/3 of an atmosphere. So I used the barometric formula to calculate that based on the altitude and the temperature. B, show the barometric pressure decreases by 2/30ths in value for every 1,800 foot increase in altitude. So this is a formula like the mountaineers would know, the people who really rely on, how much oxygen is going to be there. But what we can see is that the reason we have this is the density does not decrease linearly. If the density decreased linearly with altitude, then we can use a very simple algebraic equation to calculate the pressure. It's a non-linear thing. It goes as a power function there. And so this is the molar mass of air. What we do with the molar mass of air is we just average it. And the molar mass of air changes with altitude because it becomes more richer in lighter elements at higher elevation. At lower elevation, it becomes richer in heavier elements. And so oxygen is heavier than nitrogen. So we expect more oxygen at lower elevations, less oxygen at higher elevations, just in the mixture of air. And so the molar mass is changing too. So you really need calculus to do this because we can account for the subtle changes in molar mass. As things change, that's when we need calculus, and the density changes and this kind of stuff. So this equation is from calculus. But this will allow us to easily calculate. And so I just had part A as my usual assignment in homework. But did you see this problem in the homework? Yeah? Oh, I did assign it? Okay, that's good. I'm glad. I don't usually do part B. Part B is getting too advanced. I mean, for the map, it's a bit much. Okay. So all we do is we know what P external is and delta V. So if we want to calculate the amount of work, let's say this is 1 liter here. And so what we have is the work is equal to minus P delta V. So we started off at 0 liters. This is V initial. And V final is 1 liter. And so this is minus 1 atmosphere times V final, 1 liter, minus V initial, 0 liters. And so this comes out to minus 1 atmosphere liter. Now, an atmosphere liter is a very strange unit, right? But an atmosphere liter is a unit of energy.
Everybody has to evacuate. Oh my goodness.
Okay, sorry.
I thought we were just people outside the apartment. Oh no.
Okay, yeah, okay, we'll evacuate right now. Let's evacuate.
It's going to be fun for your class because everybody has been out there for a while.
Okay, I forgot about that.
Oh my goodness.
Well, sort of.
And I go to the other side.
Okay, we're going to resume here with this. So these are kind of weird units, but a liter atmosphere is the same thing as energy here. And so what we're going to do is we want to be able to convert that into joules. So let's do that here. Insert. And so we have a liter atmosphere. And we want to convert to joules. If you ever forget this, the conversion factor here, it's not too difficult. It's 8.3145 joules per mole Kelvin. This is R in units of joules per mole Kelvin, and then you divide this by R in 0.08206 liters times atmosphere per mole Kelvin. Then what you see is the moles cancel, the kelvins cancel, and that leaves you with joules per liter atmosphere. And so let's go ahead and do that here. We would have 8.3145 divided by 0.08206, and we got 101.32 joules, per liter atmosphere. And so we'll just round it to 101.3 joules per liter atmosphere. And so if we blew up a 1 liter balloon against the pressure of 1 atmosphere, how many joules did that take? Well, that took 101 joules worth of energy. Yeah. So we can calculate the amount of work that's done by just knowing the pressure. The pressure has to be constant, and so we're expanding a gas under constant pressure, and the temperature doesn't change either in this. And so constant temperature and constant pressure. All right, so what we're going to do is this. What we want to do is we want to be able to make predictions. We don't want to have to measure everything. We want to have to do a calorimetry experiment for everything we know. We want to avoid having to do calorimetry experiments. So it'd be much nicer just to be able to predict things. The way we're going to predict things is this. We're going to use the first law of thermodynamics, and there are two things that we really want to know. We want to know something of delta U. This is the change in total energy or change in internal energy of the system. Change in internal energy of the system. Internal energy is the total energy. Of course, the energy, according to the first law, can neither be created nor destroyed. So if the system loses or gains energy, it must have went to the surroundings. And then there's one other thing we want. We want delta H. Delta H is what we call enthalpy. And so this is the change in, this is go to the system. This is the change in enthalpy of the system. And so what we need to know is we need to know, how is enthalpy defined? How is enthalpy different than energy, total energy, internal energy? And so the first step is just to remind ourselves what internal energy is. Internal energy is the total energy. And the total energy is the sum of the potential and kinetic energy of the system. So the kinetic energy is just motion. And so this is water here. We have 3 types of motion. And so this is the kinetic energy. The kinetic energy we can calculate. However, the potential energy is a bit more tricky to deal with. Kinetic energy, we can calculate the translational kinetic energy. That's 1/2 mu squared. We can calculate the rotational energy, which you don't have the equation for. We can calculate the vibrational energy, which you don't have the equation for either. You only have the kinetic energy for an ideal gas or a monatomic species. So we'll have this translational, this is our EK, and so can calculate. However, the potential energy is a bit different because the potential energy is the energy in intermolecular attractions. We can determine that. Hydrogen bonding interactions are about 25 kilojoules per mole. And so if I have a mole's worth of these hydrogen bonding interactions, to break all of them, it would cost about 25 kilojoules in a mole of water. Potential energy will be stored in the bonds. You know, in order to break bonds, to break a bond, does that cost energy or does that release energy? Yeah, and to break a bond is going to cost you energy. To form bonds, do you know what happens when you form bonds? It releases energy. And the amount of energy that's released is the exact same amount of energy that's required to break it. And so we have energy in the bonds. Well, the bond energies we can figure out. And so I can figure out the potential energy stored in the bonds. And then we have potential energy stored in electrons. You know, to remove the electrons is called ionization. To remove the electrons will cost you ionization energy. And so if you have 10 electrons, you have to add up all 10 ionization energies to melt up all the electrons. So that we can determine. But where else is there potential energy stored? There's potential energy in the nucleus. So if we want to break apart the nucleus, we have to break apart the protons from the neutrons. How much energy is that going to cost? You know, to break costs energy, to form is going to release energy. So we have potential energy in the nucleus. And then we have potential energy in the protons. You know, you could break the protons into even smaller pieces. You know what those smaller pieces are called? Quarks. And the neutrons as well. And so it becomes quite difficult. And so the absolute potential energy, that is, when is the potential energy zero? When have I broken apart everything? You know, are quarks themselves broken into smaller pieces, or is that as small as it gets? Do you know? And so absolute potential energy is difficult because, you know, this is et cetera. And so where's absolute zero of potential energy? Nobody ever. People have come up with calculations, but the errors in the calculations are so big that the errors in the calculations are bigger than, you know, the energy associated with all chemical reactions. And so people have come up with these calculations, but they aren't so accurate. And so what we say is the absolute. This is like absolute internal energy is not normally determined. So this goes back to something in pressure I didn't really talk about, and that's gauge pressure versus absolute pressure. Absolute pressure, when it's zero, that means there's no gas, there's no collisions. So if we have a zero absolute pressure, we have empty space. However, when you have a tire gauge, you know, if your tire goes flat, the tire gauge will read zero. When a tire gauge reads zero, does that mean there's no gas? No. When your tire gauge reads zero, that means the pressure inside the tire is the same as the pressure outside the tire. And therefore you have, and so there's air. In order to get the remaining air out of the tire, you have to suck it out. Do you want to suck the air out of the tire to get absolute zero? You probably can't because your lungs aren't powerful enough to suck out all the air out of a tire. But, you know, we call that zero pressure. Now, when we do gas calculations, we have to use absolute. We have to use absolute temperature, and we have to use absolute pressure because zero means something. For gauge, like we wouldn't use Celsius because the zero doesn't really mean anything in Celsius. It just means you're at the temperature of ice, freezing water or melting ice. But the same thing with pressures. You shouldn't and you can't use gauge pressure in equations. You have to convert the gauge pressure. And the conversion is simple because it's like Kelvin to Celsius. You just add it. You add whatever atmospheric pressure is, let's say 14.7 psi, to zero. And so if your gauge is reading zero and the atmospheric pressure is 14.7, you just add it. So if your Celsius is reading zero and you add 273, you just add it. So 0 Celsius is 273 Kelvin. And so that's what we do with gauge. I think I assigned gauge. So we could do relative. Some people do relative. They ignore the nucleus, they ignore everything else, and then they just look at electrons. Or sometimes they will ignore the electrons and look at chemical bonds. We can't really ignore electrons because of redox reactions. Redox reactions, we've got to worry about that. And so we've got to worry about this. So we can get maybe relative internal energy and call it zero once all the electrons are knocked off. That might be easier to calculate, but most of the time we don't determine this. So we want delta U. So a system contains only internal energy. This just means the total energy. A system does not contain heat or work. Heat and work are exchanged when there's an energy change. And so, for example, if your system loses energy, then the surroundings will gain that energy in terms of heat and work. So if your system gains energy, then the surroundings lose that energy in terms of heat and work. So this is the energy exchange with surroundings. When we look at the energy exchange with the surroundings, it's in terms of Q and W. So when we're interested in delta U, the change in internal energy or the change in total energy, then we'd like to do U final minus U initial, but it's not possible because U final is equal to the kinetic energy final plus the potential energy final, okay, minus U initial, which is equal to the kinetic energy initial, plus the potential energy initial. Kinetic energy we can determine, and so delta EK can be determined. However, delta PE is not. The potential energy, this poses a problem, and so not easily determined. Kinetic energy is easily determined, because kinetic energy just depends on the temperature, so this is easy. And so this is never done. Never done. So the way we determine this is easily done. How do we do this? Well, if we want to measure it, we could use calorimetry. And then the work is, PV work is an easy calculation. You can calculate it. And so this is easy to do. Measuring the heat and determining the work is easy to do. And determining work is easy. And so this is how we're going to determine delta U. And why do we want to know delta U? We want to know delta U let me just give you a preview. We want to know delta U because delta U is what we call a state function. State functions only depend on the initial and the final state. And so it'll always be the same. That's the advantage of this. And so we can make predictions. Like, for example, we want to know delta U for reaction. We don't have to measure it. We don't have to do calorimetry. We don't have to calculate the work. It's always the same. So somebody else did it, and if somebody else did it, we can just use it. And so we can just find the delta U values for a particular reaction, and then use it. Yeah. Okay, we're out of time, so I need to still talk about delta U and delta H. So I think what I'll do tomorrow in the lab, since I already, tomorrow's nothing. I don't have anything. All right, what I'm going to do is I'm going to just post a video. Since we lost time here and we lost time, I'm going to just add a little video lecture to Canvas.
I thought our second class was like on the 22nd. Is that correct? But that's like a lecture day. That's like a Tuesday.
Oh, no, it's Wednesday.
Wednesday?
Yeah. Yeah, so I'm going to have to do a video catch up.